Thank you very much, Danny. That was really exciting stuff. I can't wait till my car can do all those things for me. So now I'm going to talk about the future of GPU technology. I love talking about the future because it hasn't happened yet, so we can imagine all the things that are possible. But I think one of the best ways to talk about the future is to start with the limitations of the present. Aoki-san at Tokyo Institute of Technology has done a lot of really interesting work with GPU computing. And this particular work that I have the slides here for, he's analyzing performance with multiple GPUs to solve a computational fluid dynamics problem for weather prediction. And as usual, the work that he's done has a really deep understanding of what's going on inside the machine while he's trying to do his computation. So some of the problems that he's seeing represent bottlenecks in the system. In a modern PC architecture computer, there's some parts of the system that limit data movement and limit what you're able to achieve. The PCI Express connection between the CPU and the GPU is one such limitation. The memory capacity and memory bandwidth, particularly CPU bandwidth and GPU capacity, limit the amount of data that can be stored and the amount of data that can be shared between the CPU and the GPU. And what you see is, as you're trying to solve a problem, and as you're scaling up the problem size, where you have more and more computation to do, and you have more and more data to move around, these bottlenecks are beginning to limit your ability to effectively capitalize on the computational capability that is built into the chips. So these are problems that we'd like to try to go solve. So just looking at this in schematic form, the biggest limiter is the PCI Express bandwidth, which is very small, 16 gigabytes per second. CPU memory bandwidth is also relatively small. GPU memory bandwidth is very high, but we would still like it to be higher. Could always use more bandwidth. And the trade-off is typically CPU memory is large with low bandwidth. GPU memory is smaller with higher bandwidth, and communication between them is the slowest of all. So when you have collaborative computation where both the CPU and the GPU need to operate on the same data, you have contention and you have limitation because of the flow of data back and forth. So we introduced at GTC in San Jose NVLINK, which is a technology for improving the interconnect bandwidth between the GPU and the CPU. The signaling is differential with a clock embedded in it, very high efficiency, low power, high speed signal. The programming model is the same as PCI Express with DMA, enhanced DMA kind of operations. And NVLINK will support our unified memory feature, which was introduced with CUDA 6.5. And that feature allows all of the memory in the system to be addressed by either the CPU or the GPU through a unified addressing scheme. The first generation of NVLINK will not be cache coherent. That'll be in generation 2, but you will still have the ability to share memory, both the CPU memory and the GPU memory. The speed of this connection will be 5 to 12 times the PCI Express connection at first, and we'll continue to scale that up over time. With all this additional bandwidth for communication, you can also use it for multi-GPU scaling. You can connect together multiple GPUs with multiple NVLINK connections. And so then you can begin to think of multiple GPUs as a single logical GPU resource. And the unified memory feature underlying this allows all the memory that's directly connected to each GPU to be addressed and used efficiently by other GPUs as well as the CPU. So it's really tightening all the connections between the various processors on a node in the system. We want to make sure that we're accelerating CUDA and GPU computing on a variety of different platforms. Ideally, we'd like to be CPU agnostic. We don't want to have to care which CPU is being combined with an NVIDIA GPU in order to create a heterogeneous computing platform. So we, starting with CUDA 6.5, we're supporting ARM64 for CUDA, and that is typically the most cost-effective and the most power-efficient solution, ARM with NVIDIA GPU. Historically, x86 has been the workhorse of heterogeneous computing along with GPUs, a very wide deployment, but it is neither the most cost-effective, nor the most power-efficient, nor the most performant. The most performant CPU implementation that we'll support is Power CPU from IBM, and we plan to have full CUDA support as peers for all these different types of CPUs. So the other innovation that we announced is 3D memory. And for the first time, we will be building and assembling chips on top of other chips in order to build an integrated computing system with memory built into it. And that will allow us to have many, many more pins and much more bandwidth per pin, and more chips, more area for more memory capacity. So many, many times the memory bandwidth, at least 2.5 times the capacity of memory. So we will get over the limitation of restricted amount of GPU memory. And due to our signaling technology, we expect to see 4 times the energy efficiency for transaction cost per bit. So if you look at the curve on your right, the solid line represents the growth in memory bandwidth using the conventional memory packaging technology. And you can see that the growth is starting to level off. We're starting to see not only a limitation, but a slowing and improvement. And with the new 3D memory technology, we expect to move to the dotted line curve where we can begin to see much greater improvement over time. And the sky's the limit. We can have much larger, much faster memories. So we can eliminate these bottlenecks. So NVLINK for interconnection, 3D memory for memory bandwidth and capacity, and unified memory so that all of these resources can be addressed efficiently across all the processors. Those 3 innovations will be combined to build our next processor architecture. And as you probably know, we have a habit, and we prefer to name our architectures after famous scientists who have made great achievements that we are impressed by and we admire. And so we aspire to create great things as well. So this architecture will be called PASCAL, named after Blaise Pascal. He was a mathematician in the 17th century, and he made many of his inventions and discoveries while he was still a teenager. He invented the mechanical calculator. He invented probability theory. Maybe he had a friend who had a gambling problem. He wanted to help out. He described Pascal's theorem, named after him, which describes how if you pick 6 points on a conic section and connect them together with line segments, the intersections also lie in a straight line. This is a very widely used theorem in projective geometry. And finally, Pascal's law of hydrodynamics, which states that in an incompressible fluid, when you increase the pressure at one point, the pressure increases equally at all the other points. And this is used in hydraulics and many other kind of fluid mechanical devices. So truly an impressive scientist, and something we're proud to borrow his name for our next architecture. So what is this PASCAL? So this is the PASCAL computer module. I don't have one of these to show, unfortunately. There's only one, and Vincent has it. But we're going to build it. We're going to build a lot of them. This is the culmination of bringing together this NVLINK technology, 3D memory technology, and it'll be a fully self-contained computing module with the GPU chip, CPU, potentially, and the memory, 3D memory packed on it. So it's very small, very computationally dense, a third the size of a current generation PCI Express card. So what will this be capable of? We expect with Pascal to be able to continue our tradition of exponential growth in performance. Although, as I mentioned earlier, for CPUs and many other kinds of technology, we've reached the end of Moore's law and an inability to continue exponential growth. But with the innovations that I've described and some other architectural features, we expect that Pascal will be able to continue this exponential growth pattern. And so what I'm showing here is the historical performance for single precision SGEM, normalized performance, and simulations for the projected performance of Pascal, showing that we'll be able to achieve very exciting levels of performance. So what you might ask, what are we going to do with all that computational capability, all that memory bandwidth in this wonderful new Pascal system? Well, really, we'll bring the technology, and the rest is up to you. It's the expectation is that we'll continue the partnership. We'll build the substrate. We'll work with you to solve your problems, to invent new things, to create the future world. So let's work together and show the world what's next. Thank you very much.